Post. Okay, when it comes to hypothesis testing, so also correlations are hypothesis testing, and you're testing basically against a null hypothesis that there's no correlation in the data. So step one, you identify the populations, you identify the distributions, you make your assumptions, normal distribution, randomly sampled, homoscedasticity, so that you don't have no scatter at the beginning of the line and then a lot of scatter at the end. So there's homoscedasticity, one of the assumptions. Then you determine the characteristics of the comparison distribution. You determine critical values or cutoffs, as we will see in a bit how that is being done, because we're again calculating a t based on the correlation coefficient. Then we're calculating an R, that's our test statistics, and based on that, we make a decision. So today's example, does skipping class relates to the exam grades? So we have here data of 10 students. They have a varying number of absences from class, and they have a varying outcome on the exam. So basically, we will get this now into Excel, and we have a spreadsheet that is on Canvas. That basically allows the quantification of absences and exam grade. And we have exactly that data here in Excel. So first, let's start with the scatter plot. So if we go on, we're just selecting the two variables. We're going in insert. We're searching here for the scatter plot, and we're getting the scatter plot right there. So that's basically the association. So we can see already when we look at this association, there's some trends downwards. So it kind of indicates that there's, in some shape or form, a negative correlation. And we will quantify this in the following. So we can now make this a little bit more aesthetically appealing. Exam grade as a function of absences. We put in our x-axis. It's absences. Oops. Absences count. We put in our verticals. I'm going to put in here exam grade in percent. So basically, this gives us an overview and gives us an idea already in which direction we're actually expecting the association to point. And now we're going to quantify it. So if we just, let's start with kind of, so we have one population, we have 10 sample students. We're calculating now average of these 10 students' absences. So that's our average. We calculate the standard deviation. That's basically B2 to B11. Now we're basically quantifying the exam grade, so 76 plus minus 16. So we know now that there's quite some variability. So it will be interesting to quantify this. So firstly, we're calculating now the deviations. So we remember the formula. The formula basically asks first for the sum of the product of the deviations. And then in the denominator, we have the square root of the product of sum of squares x and y. So we are now quantifying x minus mx, which is basically x minus mx that we need to log in. And we need y minus my. Oops. That's basically this minus this. Now we just need to go all the way down with this formula. Gives us an overview. So now we need the product. So that's x minus mx multiplied by y minus my equals this multiplied by this. Now we just need to sum this up, and that's our numerator. F2 to F11. So that's our numerator. So basically, we are calculating the deviations for x and y. We're multiplying those. We're getting the product. This product, basically, we're summing up, gets us to the numerator. So now getting the sum of squares now simple because we have already what it takes. So we have x minus mx squared. Then we have y minus my squared. So we're basically calculating this squared. We're calculating this squared. Now we just need to pull this down. Basically gets us now to summing that up. That's our sum of square. That's G2 to G11. That's sum of square x and sum of square y. So that's now sum of squares, and the denominator is now the square root of this multiplied by this. So we have now minus 304 in the numerator, so that's this part. We have 357, which is this part. Now we just need to calculate this. Oops. Equals this divided by this. So we're looking at an R of minus 0.85, which is consistent with the inverse relationship that we have expected. We know that this is, as per our convention, it's a large correlation coefficient, which seems quite solid. There's not that much variability. And that basically completes our task. So now lastly, we want to do a hypothesis test. So we want to know whether this is a significant association. And we're doing this by, where are you? We're doing this by basically calculating this formula. So that's how you calculate the T. Oops, too large. So now we have T equals R multiplied by square root of the decrease of freedom. The decrease of freedom in a correlation is quantified as the number of participants, so the sample size, minus the number of variables involved. In a bivariate correlation like this one, there's only 2. So that means n minus 2. If you have more than 2 and you have a multivariable regression analysis, for example, you would calculate minus 1 for each variable. For now, it's decrease of freedom. Divided by 1 minus r squared, we're getting to that on Wednesday. The r squared in regression analysis and in, well, as the basis always in correlation, basically indicates the amount of variability that is the proportion of variability that is explained by the regression function. So if you remember from the ANOVA was r squared and eta squared, we knew what proportion of our variance of the total variability, the total variance was attributed to the variance between the groups. So what fraction of that was accounted for by the differences between the groups, or the variance between the groups. Same concept applies here, because you're fitting a line through a scatter, through a cloud of data points, and you want to know how much can I actually explain by fitting that line through, how much scatter is left after I fit that line through. So you have explanatory power, and that explanatory power is quantified as the r squared, which essentially is, as we will see later, the correlation coefficient squared. which incorporates all this information in a raw form. So 1 minus R is basically the unaccounted variability. So that's the variability that was not explained by our regression function. So we're getting correlation coefficient multiplied by the square root degrees of freedom divided by unexplained variability. So if we have R, so R square logically is then just this squared, which is 0.72. So now if we want to calculate the T, and let's go first to the T-score table, because we have a degree of freedom of 8. We're after a p-value of 5%. With degrees of freedom of 8, p-value of 5%, we're at a T-score of 2.31. That's our critical value. So critical value is 2.31. Our T is now R multiplied by square root degree of freedom, that's 8, divided by 1 minus R squared. So we have a T of minus 4.6, which clearly is greater. So we're rejecting the null hypothesis, which we know is HO is there's no correlation. HA is there is a correlation. So if there's no correlation, we know that R equals 0. So that's our null hypothesis, R equals 0. Or alternatively, our line of best fit is a flat line. So we're rejecting the null. We're saying here's a significant correlation found in our data. So we know from that that absences do count, and the exam grade will get worse if students are not coming to class. Yes.
I was a strong correlation coefficient.
Yes. So there were conventions. Remember the conventions? Yeah. 0.85. Yes.
Here's something that we already knew. Has a strong correlation coefficient.
Not necessarily. Not necessarily. You remember when we had, for example, the discussion with the effect size. So the effect size takes out sample size of the equation. So sample size will affect your variability because it's relatively less variability if you have a large sample size. So if we, for example, if we see a correlation coefficient with minus 0.85 in a sample of 4, it's less likely to be significant as compared to a sample size of 150. So it's really, this is where the sample size and the variability comes into play, because sum of squares will be different, will still be a lot, but in relative terms, it kind of will then equalize, because you have the numerator, which is the product of the deviations, divided by the product of the sum of squares. So this is where sample size is definitely affecting the probability of this being significantly different. But good question, thank you. Really good question. Okay. All right, so this is basically what we had on calculations today. So any questions on this? So again, we're doing deviations. We're calculating the product of the deviations. We're summing them up. We get to a numerator. We have square deviations for each of our entries. We're summing them up. We get sum of squares of X and sum of squares of Y. We're square rooting the product of that, gets us to the denominator. The ratio of these two, dividing numerator by denominator, gets us to an R. Squaring this R gets us to an R squared, and we can also utilize this to calculate a T, which allows us to hypothesis test this association as either being significant or not significant. Good. Okay, back to the concept. Okay. So it's the sum of the products of the deviations for each variable is divided by the square root of the products of the sum of squares for each variable. This calculation has a built-in standardization procedure, and this is what I meant with it basically fits that line through. Think of it as the line of best fit. It fits a line through. You basically have that variability around that line. Remember the same concept as the ANOVA, where we had kind of this variability between the groups and the variability within the groups. Same concept applies here. So you basically have variability around that line of best fit. And there is some inherent standardization that you basically standardize the scatter then to the line. So you basically, in the end of the day, what you're quantifying is the so-called residual, which is the distance from the line to the data point. And this residual is just this difference. And these differences are standardized and are distributing around the line of best fit in a normal distribution. And this is where the T is coming in, because you have a standardized normal distribution. And this is how you determine whether the correlation association is significant or not. Okay. Any questions on any of this? Good. Partial correlation. So we talked about this already a bit. So we talked about ice cream drowning and ambient temperature. All of this points towards that there are unknown additional variables that cause an effect on the dependent variable, which could be parallel to an effect of the independent variable, or could be associating the independent variable, and that's how the independent variable associates to the dependent variable. So you're mapping this out in a directed acyclic graph, as I showed you the Daggett website. So when you assign correlations to that, you establish correlations between two variables, between those pairs of variables, and you can thereby eliminate the effect of one. You remove that correlation from a causal pathway to basically can quantify now all of these, and you can basically get this jointly to quantify these intersections. So it's basically, if you have weekly hours of tennis, you likely have a higher number of weekly hours of tennis if you have a higher longevity in years. If you have weekly hours of tennis, you're more likely to bet tennis when you have more years of education, not impossible. If you have many years of education, you're also more likely to have more longevity in years. So it's somewhere in these lines, and these partial correlations are basically the combined factors, where basically B is explained by A and B between this pathway, and basically all of these where they're intersecting basically a sum of all these variables associating with each other. So you can break the association up into various subsegments where they're intersecting. The way of depicting here, that's called a so-called Venn diagram, is a very, very elegant way to actually depict data, particularly when you quantify populations and you want to understand which populations are basically overlapping in some shape or form. Any questions on that? So lastly, we have now psychometrics. So we talked about psychometrics already a little bit. We talked about reliability and validity. So psychometrics is actually, it's a science by its own right. So nowadays, particularly now in these days, it becomes more and more mainstream. It becomes more and more ubiquitously used. In clinical medicine, it becomes a quite standard procedure to quantify with questionnaires the well-being, the quality of life, the general health perception of patients. It's actually even part of some of the Medicare reimbursement schemes. So you basically, you have this just all around you, and these assessments are quite standard. In psychometrics, or in psychology, they're very common. So psychometrics is really it's the technique to measure psychological outcomes. One of the oldest one is like, oh no, that comes on Wednesday. One of the well-known, older well-known assessments is the Beck depression inventory, for example, that has been used for decades now to quantify depression. We will have an example on Wednesday, and I actually have the original publication for you to review. Psychometricians are actually the experts who are putting these psychometric assessments together, and they're basically interested in two dimensions: reliability and validity. Reliability is basically how consistent are the outcomes of that assessment, whereas validity is how accurate is that assessment. So both are extremely important, as you can imagine, and there are different ways to test these. So a reliable measure will be consistent. That means if you measure this today, you should also measure it in 2 weeks, and it should yield the same results. You can do this with the so-called test-retest reliability. So when a scale is being used to provide consistent information every time the test is taken. Then you have the split half reliability that is basically used. Let's say you have a questionnaire with 100 questions that basically quantifies one outcome. That means that each item in that questionnaire kind of needs to point towards the same outcome, right? So one way to test for this with this split half reliability is to take the odd numbered questions and take the even numbered questions, and then correlate the outcomes. And if there's a correlation between these two dimensions of that questionnaire, you can say, okay, so this is reliably measuring that particular outcome. So you use that internal consistent result and that association to see you have a reliable measure at hand. The more advanced format of that is in population studies where you have a sample, you have questionnaires within a sample, you quantify the so-called coefficient alpha or Cronbach's alpha. That is basically also used to estimate a reliability in a population where you have administered that questionnaire. You basically now taking the average, so you have for each individual, you calculate odd and even numbered results. You build an average, and then you use that in the 100 people you have tested this, and you correlate these averages. That gives you a population-based Cronbach's alpha, which is essentially nothing else but a correlation and will vary between 0 and 1, where 0.75 indicating that it's an internally consistent questionnaire in that population you have tested it. So it's kind of a quality measure for that psychometric tool that you're testing in your population. It's a validation concept. Yeah, validity is you're trying to find out, is this a valid tool to measure that outcome you're interested in? So if you, for example, you quantify perception of health of an individual or quality of life, and you get a number, at the end of the day, you assume that number will stand for something, and you have a population of 100 people, you would need to assess whether whatever you assessed with your quality of life score really indicates that that individual really had a good quality of life. One way to do that is, for example, and these are classically, so if you have perception of health and you correlate the score of perception of health with the number of times that individual, that the population, each individual in the population was in the hospital, and there's an association, an inverse association, you know that this is a valid measure that indeed measures something that has to do with health. So that's kind of how you have to think about that. So that's validity. Okay, so reliability and validity. And then we have lastly, and Nolan and Heinz wanted to make that point, that personality quizzes that you find in magazines and journals are rather doubtful validity and reliability, and are more or less not to be taken too seriously. They're more for recreational and entertainment purposes rather than really reflecting psychometric assessment. Good. Any questions on that?
For sure. I think BuzzFeed quizzes are very reliable.
Yes, certainly, certainly. Any questions on that? Any of this? Okay, then we can slowly talk about the last topic and go back to our spreadsheet. I just want to set the stage for regression on Wednesday. So we have now our scatter plot. So that scatter plot basically is determined by an association, which essentially is quantified as a t and the correlation coefficient. One way to think about that is by basically fitting a straight line through that. So if you fit this line through, that's the often quoted line of best fit. So that's basically the line of best fit, fitting through that scatter, basically showing an association that essentially is inverse. If we click again on the trend line, we can now display in Excel, we can display the equation as well as the R squared. So you all know from high school how a linear function is basically quantified. So you have a y, which is the dependent variable, expressed as slope multiplied by x plus the intercept, the starting point of that line. So wherever x equals 0, that starting point, that's your intercept. That's here at 94. So if you were to quantify all of this, you could simply do this also by quantifying the slope with the slope equation, which is basically y2, which is the second y, minus y1 divided by x2 minus x1. So this is basically the ratio between the distance from this point to this point, and then from x from this point to this point. So the way you could calculate this, if we say, okay, x equals 0, that's like somewhere in the realm, that's 94. Then we have x equals 1. That's basically at x equals 1 is somewhere in the realm of like 94, let's say like 89. Then we have x equals 2. That goes through somewhere at 84. So if we, based on that, want to quantify now y, oh no, that's the one. So if we were to calculate now the slope based on that, the only thing we would need to do is to calculate y2, let's take the 84 minus 89 divided by x2, which would be 2 minus 1. So that would basically be nothing else but slope minus 5 divided by 1 is minus 5. So now this is a very rough estimate, this minus 5, but it's basically as consistent with what we see here on this equation. And so that's how you can by hand calculate the slope. It's just important to keep that in mind for the exercises we're going to do on Wednesday. Okay, so this is basically this. What else do we have to discuss? For some interesting reason, I'm always faster with you guys. Okay, so we have exam grades, we have the slopes, we have quantified the correlation coefficient. We calculated this is the sum of the deviations of x and y. as a ratio between the sum and the square root of the sum of squares of x and y square rooted. We utilize this essentially to quantify our r. We can then, by squaring, we can calculate our r squared. And so the way you have to think about the r squared, and this is skipping ahead a bit to Wednesday's class. So we have total variability, and this total variability is basically the variability of the entire scalar. If you're fitting a line through that, so this is the variability from here to here, from here to here, so this is a large value. If you fit a line through that and you know where this line is starting and you know the slope of that line, you're kind of explaining some of that variability. So the distance from that line to the individual point is smaller as compared to the overall variability from the 0 point. So you're explaining part of that variability. And the part that of the variability that you explain, this becomes kind of the regression variability, which is quantified as the distance of each individual data point to the line of best fit. The leftover variability remains the unknown, unexplained variability. The proportion of that, which is explained away by fitting that line through, basically is our r squared, which is logically, because we're basing it on only 2 variables, was a bivariate correlation like that, easily calculated by squaring the r. If you have more variables, this becomes a little trickier, because at that point, you will need to factor in all the variables that explain even more of that variability with that additional information for each data point. So the residuals will get consequently smaller, and consequently also the r squared will get larger. So this is this aspect that is to be kept in mind. So that's the r squared. So we have here the residuals is basically the distance from here to here. And what I mentioned before, we have this standardization involved in the process of calculating the r. And when you look only at these residuals and you would plot only those residuals, and in regression analysis, and we're going to do this on lab day, you can actually do that quite simply. You can basically create a histogram of the residuals, and that histogram of the residuals will basically follow a normal distribution. And this normal distribution is basically the standardized distribution of these residuals, which is being used for quantifying the t distribution here at this point. So we're calculating a t based on the distribution of these residuals and use this t for either accepting this as a significant correlation or not. That's basically the aspect of the t. So everything evolves around these residuals. And what's also important to keep in mind, the assumptions of a correlation or a regression more specifically, it's important that these are A, following a normal distribution, B, are randomly sampled and independent measures. So each of these data points is an independent participant. And lastly, they need to be homoscedastic. You remember how do we have homo and heteroscedasticity with the groups in the independent sample t-test, where we basically were quantifying the variance in each of those groups. And we also did it in ANOVA when we needed to have comparable variance between the groups. The same applies here by basically the assumption that all of these data points, all of these residuals, the distance of the individual points to the line of best fit needs to be somewhat comparable across the entire range of that line of the data. So, which is funny because essentially Nolan and Heinzen give you an example, and I didn't want to mention it first. Bless you. This graph is actually violating exactly that principle, because you have here so much variability and so much data, whereas here the following, you do not have this data. And when you think about how this line of best fit and the slope and the correlation coefficient is quantified, you will have here a regression. So that line will always gravitate towards where you have most data, because the mean will be basically kept in that area because you have most data there, and it will gravitate by the calculation of that line always towards the bulk of the data. Whereas this area where you have less data, it will always gravitate towards the outliers, because you don't have this massive amount of data that kind of keeps the function stable. And this is a phenomenon that is called the regression to the mean phenomenon that we will talk about on Wednesday in more detail. But basically, this is actually a terrible example for a terrible graph as an example. And they indicate here, for example, they indicate these outliers. And these outliers are actually to be kept in mind, because you will see a lot of outliers. And these outliers, particularly in areas with little data, they will always kind of change the slope of your function, which is sometimes quite tricky. The problem with outliers is that you can't really do much about them. You would be tempted to kind of just exclude them, but you end up not being able to do so, because just you need to have really solid justification to exclude outliers, and that's science by its own right. So you need to be very transparent about what outliers you excluded and why you did it. And statistical reviewers are not going to be happy in that, so you better have a really good justification ready. That's the story about outliers. All right, so I guess we're through it. Any questions? No? All right, then we can conclude for today. Have a nice evening and see you on Wednesday.
Thank you.